Hello everyone, welcome to Bioorganic Chemistry course. Before we move to the actual content of the course, I thought it's useful to refresh some of the basic concepts related to chemistry, especially organic chemistry. And this concept will help you to understand the bioorganic chemistry better. It will also enhance and facilitate your learning. It's good if you're aware of some of the concepts such as chemical bonding, functional groups in organic chemistry, chirality and stereochemistry, and some knowledge about isomer, enantiomer, and diastereomers. Importantly, some of the reactions of alcohols, aldehydes, and ketones. Specifically, the oxidation reduction, enamine reaction, ketoenol tautomerism, configuration and conformation in inorganic chemistry, stability of cyclic systems, and optical rotation. Let's start with the chirality. Chirality was first proposed by Lord Kelvin back in 1904. According to Lord Kelvin, any object or geometrical shape is chiral provided it has non-superimposable mirror image. And chiral objects are ubiquitous in nature, and they are very important in understanding and the evolution of life and origin of life. Chirality can be found in molecules, in macromolecules, and any given object or shape. Chirality is the geometrical property of a molecule. A chiral molecule cannot be superimposed in its mirror image. That means it has a non-superimposable mirror image. Any molecule or object has a mirror image. What do you mean by superimposable? In a simple way, a superimposable means all atoms bonds in a molecule can be simultaneously aligned with identical atoms and bonds in its mirror image. That the mirror image of a molecule is identical to its original structure. Such molecules are achiral and they lack the chiral center, as an example here of methane. Chiral molecules, molecules with one stereogenic center is chiral. Any molecular object that cannot be superimposed on its mirror image is chiral. The relationship between a chiral molecule and its mirror image is known as enantiomeric relationship, and the resulting two structures are called enantiomers. Here is an hypothetical structure of a carbon attached to 4 different halogen atoms. And the mirror image of this structure is shown in the right side. And if you try to bring them together, you will clearly see that they are not superimposable. The difference in the previous slide about methane and this is that here the carbon is attached to 4 different types of atoms or groups. And if a molecule has one stereogenic center or the chiral center, what about those have more than one chiral center? More than one chiral center containing compounds may be or may not be chiral. And for that, we need to understand a little bit more about the representation of the molecule in 3 dimensions, and that is called stereochemistry. Stereochemistry is the study of relative arrangement of atoms or groups in a molecules in 3-dimensional space, just like as shown here for a methane. And this is how a conventional projection that we write in 2D plane, and this is the real 3-dimensional structure of a given molecule. And more detail, we use variety of representation, and these representation are projections. Projections are the way to represent a molecular structure or bonding, position and orientation of atoms or groups of a 3D molecules or objects in 2-dimensional plane. And you might have already studied Fischer projection, source projection, and Newman projection. And in Fischer projection is important in the beginning to understand the carbohydrate chemistry and how to write the structures. Fischer projection is a way to represent three-dimensional molecules as a flat structure. As an example, here is a conventional representation of a chemical molecule, and you can transform the same structure into a Fischer projection, and the Fischer projection can be transformed into a flying wedge representation that we will use a lot. And here the dashed bond, which means these groups are pointing away from the viewer or you, and the thick wedge-shaped bonds means those groups are pointing towards you. The molecules that have the same chemical formula and bond connectivity, but they differ in the relative arrangement in three-dimensional space, are called stereoisomers. And chiral molecules have one or can have more than one stereoisomers. And stereoisomers important because they can have different properties, such as R and S limonene. The R limonene is present in orange and S limonene present in lime. And these two are good examples for stereoisomer, and they are related by their mirror image. And only different, they have same chemical formula, but their relative arrangement of this particular group here is different compared to this. But how to determine whether a given molecule is chiral or not? And for complex molecules having more than one chiral center, this is not straightforward. However, there is a certain theory, what we call as group theory, a mathematical concept that can be applied to determine the symmetry elements in a molecule. There are 4 symmetry elements which needs to be considered, and you don't need to study them if you have not studied, but it's good to know that this kind of theory exists and concepts exist. And those 4 are center of symmetry, plane of symmetry, axis of symmetry, and rotatory deflection axis. We can discuss a more detail using molecular modeling software or using actual model in the classroom. The other important point to know is enantiomers. Enantiomers have some of these properties such as identical melting points, boiling point, solubility, index of refraction, and similar spectral pattern when you use a achiral solvent that is not chiral. But enantiomers can differ when they interact with other chiral substances or when they interact with a plane polarized light. That's called optical rotation. When only one of the enantiomer is present, then such compound is called enantiomerically pure. But if a compound contains both enantiomers and equimolar mixture, then these are called as racemic mixture. The other form is called Meso form. As an example, here is tartaric acid, which has 2 chiral centers. Theoretically, one would expect there are 4 stereoisomers. However, there are only 3 stereoisomers because this molecule here shown is a mirror image of this. So these two are related by a mirror image. If you draw a line, you will see that these are therefore enantiomers, D and L tartaric acid. The other structure you can write is the hydroxyl group on the same side. And the mirror image of this will be hydroxyl group having on the other side the same. However, because this structure has an internal symmetry, if you draw a line, the top half of this molecule is the mirror image of the bottom of these molecules. Therefore, this kind of structures are called meso structures. They have stereocenters, but they are not chiral because they have internal symmetry. The third form is diastereomers. Here, in this structure, you have 2 chiral center. And important to note is that bromine and chlorine pointing towards you. And this structure, the bromine and chlorine are pointing away from you. So you have a mirror image of this structure. Mirror image of 1 is represented by 2. So these 2 are enantiomers then. You can also write 2 other structure, they are related as enantiomers. However, if you take structure 1 and structure 3, these 2 are stereoisomers. However, important to note here is the arrangement of atoms in this chiral center is same in both 1 and 3. However, if you notice in this chiral center, then the arrangement is slightly different. You can clearly notice bromine and hydrogens have interchanged their position. That means they have they are stereoisomers, but they are not having a mirror image relationship. And such molecules, such stereoisomers, are known as diastereomers. Diastereomers, unlike enantiomers, have different physical properties such as melting point, boiling point, and solubility. So diastereomers can have same configuration at one stereocenter, but opposite configuration at another stereocenter. So now what is configuration and what is conformation may often confuse you. The configuration of compound is unchanged until unless you break a bond and make a new bond. And it has to happen at the stereocenter. Here, for example, to make from this molecule to this molecule, you need to break and rearrange. Conformation, on the other hand, can happen in any molecule continuously under ambient conditions, say at room temperature, for example. It is due to the rotation about single bond and flipping of the rings. Here is N-butane and here also N-butane. Only difference is that this is rotated around the single bond. This free rotation will result in a multiple conformation. So a stereoisomer has always a single configuration, but it can exist in a multiple conformation due to the free rotation around single bonds. Now the next is absolute configuration, and these are denoted using R and S. R stands for rectus, that means right-handed or clockwise. S stands for sinister or left-handed or counterclockwise. In this case, you need to assign to determine the absolute configuration, you need to assign the priorities to the atoms directly bound to the stereocenter. When you have higher atomic number, they get the priority, such as shown in this order. If you have different isotopes of the same atom, such as shown here for a hydrogen, deuterium, and tritium, then the one with the higher atomic mass takes the priority. What happens if there is a tie? Then the next atom in the chain is used as a tiebreaker. And if you take here, for example, here's a bromine and another bromine. So of course, this group gets the priority. Then this in this way. So if you consider like here is a carbon attached to hydrogen, 2 hydrogen, and carbon attached to only 1 hydrogen, carbon attached to all 3 methyl group, carbon attached to 1 chlorine atom. Because the chlorine is immediately connected to the carbon, this gets the priority compared to this group. And now the bromine has higher atomic number, so that gets the priority. The priority decision is made at the first point of difference. The first point of difference is here. So even though this has hydrogen, but because the chlorine is here, this gets the priority. We can also discuss in the class in more detail if you are not able to follow this. What if you have the double bond and triple bond? And then you have to treat each bond as separate atom. You have to duplicate and add an imaginary atoms. And the rule is such a way that if you have a carbon-carbon double bond, then you add a carbon as an imaginary atom. If you have carbon-nitrogen atom, then you add a nitrogen and carbon as imaginary atom. If you have a triple bond, you had three carbon atoms. If you have a carbon and oxygen double bond, then you add carbon and oxygen. And this way you can assign and give the priority number. Let us look into how we can determine the R and S configuration. And here is an example. And these two compounds are related by their mirror image. And now bromine is number 1. And because of the higher atomic number, after bromine comes oxygen. After oxygen comes carbon and metal group here. And finally hydrogen. And remember this dashed bond, it means that hydrogen is away from the viewer. So in this way, if you consider now 1, 2, 3, it is going in a clockwise direction. And the other isomer here is the bromine is here, oxygen is here, carbon here, hydrogen. So 1, 2, 3, 4 is going in anti-clockwise direction. So this we can say this is R and S.